Hello, good afternoon, everyone. Thanks for joining the New Zealand Society for Earthquake Engineering webinar. And the webinar is on why is seismic design in New Zealand so hard. So that will be presented by Michelle Grant, who probably doesn't need any introduction, but she's a director at LG Consulting Limited. And she's also been on the Seismic Risk Working Group and is a former president of CSOC. Just a bit of an introduction about the webinar. Michelle presented this talk, or a version of this talk, at the recent New Zealand Society for Earthquake Engineering conference last month. And that was well received, and there was a standing ovation for Michelle on the talk. The talk challenges some ways in which we do seismic design and our standards. And as a society, the New Zealand Society for Earthquake Engineering is keen to support these debates and discussions so that we can enhance how we practice seismic design and earthquake engineering and improve that so that we can improve the resilience of New Zealand to earthquakes. So I'll now hand over to Michelle, because I'm sure there are some almost 1,000 people registered for this talk. And it was important to open this talk and the discussion wider than those who came to the conference. So hence the webinar. Michelle, over to you now.
Thanks, Brabha. Good afternoon, everybody, and thank you for joining me here today online. As Brabha said, I originally was presenting this as a paper at the NZSEE conference in a time slot that was reserved for an update on the Seismic Risk Working Group. However, the suggestion was made that I instead present this paper that I had authored to all of the attendees at the conference, with the idea that it would hopefully generate some discussion and some ideas as we start to look forward in New Zealand in terms of our seismic design pathways and compliance methods. I work in a small office in regional New Zealand, designing pretty normal stuff, normal buildings and structures. Over the last 2 years, I have been lucky enough to be involved with the Seismic Risk Working Group. And when you do these sorts of roles on standards and you start looking at overseas standards a little bit more, you start to look more closely at our standards and how we do things. And I kept coming back to one question, which was, why is seismic design so hard in New Zealand? And before starting, I want to say that this is my opinion as a practitioner in a small town working on normal stuff, normal buildings, normal projects with average software. And I can say with a reasonable level of confidence, it's not the collective view of the Seismic Risk Working Group. In New Zealand, we have a Building Act. And the Building Act sets out the goal that people can use buildings safely. That's priority number one. To achieve this in the design of our buildings, we have our 3 compliance pathways. We have acceptable solutions, we have our verification methods, and we have our alternative solutions. One is a pre-packaged structural solution, whereas a verification method requires a higher level of skill and following some methods and procedures. And the other is alternative solutions, which tend to be for things that are a little bit more outside the box. So we have a pre-packaged structural solution, a method that requires more skill following methods and procedures, and something that's for things that are a little bit outside the box. My focus today in this presentation is on the main pathway that design engineers use, which is the methods provided within the verification method pathway. In a seismic context, design standards for provisions, so in a seismic context, design standards for engineers include provisions for seismic systems in buildings for systems to resist lateral sideways forces, a lateral force resisting system. And the development of a lateral force resisting system is quite a process. A seismic lateral force resisting system is a lot more complex than a gravity support system. It requires a well-configured system detailed for an inelastic mechanism to safely dissipate seismic forces. And the development of an acceptable lateral force resisting system starts with a concept idea. These systems take decades of research, testing, and refinement before they're adopted into our design standards. If we take an eccentrically braced frame like this, a steel frame for example, the development of these goes back to the 1970s in Japan, with further testing in the United States at Berkeley University through the 80s, and guidance provided for New Zealand design engineers with R476 in 1995. There's quite a journey, a proper journey from concept to code. We design these systems using our design standards, our codes, and then we go out and we observe how the system worked in real-world earthquakes. We look at what happened and how it behaved. After this, we usually head back to the lab and we do some more research and some more refinement, which inevitably leads to updating our design standards and eventually citing these updated standards in our verification method. And we do all of this work to provide a verification method compliance pathway for designers to use. So let's look at our design standards. One of the most important things when you write a report or a design standard is knowing who your audience is. Who are we writing this standard for? This bell curve shows the spread of grades of students studying introductory structural mechanics at the University of Auckland in 2022. It's a random data set that I've used because it was easily available online through an OIA, but it's just an example of the spread of abilities of a group of people. And it shows that not all students achieve an A grade. It's fair and reasonable to assume that the same spread of abilities would be reflected in the engineering profession. Not all of us are A-grade students. The majority of engineers would be fair to assume are competent but not experts. We then need to consider what is being designed. What are we designing all day, every day in New Zealand? Stats NZ collates information on construction in New Zealand. And they group this information for buildings into two main categories of residential and non-residential. And it has subcategories as shown here. It also breaks the information down by geographical region, so you can get information for each of these subcategories across different geographical regions in New Zealand. In the year ending September 2025, the value of consented building work in New Zealand was just over $26 billion. And 2/3 of this, a fair proportion, is made up of residential construction. Standalone housing made up $11 billion, a total of 41% of consented building work. Non-residential construction made up the remaining $9 billion, or 1/3 of consented value. And we can make some assumptions and interpretations of this data if we look at the geographical spread and these categories. And if we do this and make these assumptions, we're led to two important observations. One is that most construction in New Zealand is residential, and two is that most of it is low rise. So where does this get us to? The reality is that most buildings in New Zealand are being designed by competent but not expert engineers working on low-rise buildings. Let us now turn to the design of structures for earthquake loads. For this presentation, I have compared our New Zealand design requirements to those of the United States of America, which do tend to follow a more prescriptive approach. The New Zealand standard has some quirks, shall we say, when it comes to the derivation of our loads. We have a somewhat overly complex and inconsistent load treatment. New Zealand standards require live load to be included with both usage and area-based reduction factors. We also have an additional 8% roof mass lumped at the top, creating a more complicated process with significant variability that does depend on engineers' assumptions, particularly around superimposed dead load. There's some very different approaches to this in New Zealand. The area reduction penalises small structures, and if you combine that with certain occupancy categories, it can cause live load to dominate seismic demand in lightweight buildings, despite these loads not being representative of actual seismic mass. If we compare that to the USA approach, where they have a simple uniform superimposed dead load prescribed, live load is largely excluded from seismic mass. New Zealand's method is less transparent and can lead to inconsistent outcomes. They also don't have the 8% lumped mass in their structures for equivalent static. Once we have our loads, our demands, the first step in the design of a seismic system is choosing which lateral force resisting system to use. In New Zealand, the loading standard 1170.5 does not prescribe lateral force resisting systems. The description and definition of a lateral force resisting system is designated to the material design standards, which have varying approaches. But for a design engineer, the focus at the start of the design process is on adopted ductility, not on the choice of lateral force system. Material standards also provide different compliance pathways in how they present this information on the different system. Across the steel, timber, and concrete standard, we're generally defining components, generalization, and expecting engineers to design the systems themselves. And you can see this across all three of the main materials. Each takes a slightly different approach or a different approach to achieving an inelastic mechanism at the system level. For steel, 3404 sets out seismic design requirements for braced and moment frames, with detailing in Chapter 12 and ductility values in Appendix B. This standard's probably at the more prescriptive end of the New Zealand framework. For concrete, 3101 requires engineers to identify potential plastic regions. It defines limits on strain and curvature ductility via the KD factor, which is linked to overall system ductility. For timber, 1720.1 introduces the concept of capacity protected elements and potential ductile elements, and it leaves it to the design engineer to determine how capacity design is to be applied. Very much a first principles approach to the design of a lateral force resisting system. When it comes to mixed material systems, things become more complex. Engineers must interpret across multiple standards and apply sound judgment to ensure the fundamental principles of each material is satisfied. This lack of clarity is leading to significant inconsistencies in approach, and these are very common systems being used more and more frequently across New Zealand. Notably, I haven't even touched on NZS 4600 for cold form steel or NZS 4230 for reinforced masonry block, even though both of these standards are widely used for low-rise buildings in New Zealand. We also don't have clear limits in New Zealand on when a designer can use a certain system. And this leads to engineers designing structures, for example, as this one here, with plasterboard walls providing support to masonry block walls out of plane. Plasterboard walls holding up something very heavy out of plane. Another common example is non-ductile cold form steel frame structures supporting heavy, tall precast concrete panels, which you see on industrial and commercial buildings across New Zealand. In comparison to the New Zealand approach, the USA Loadings Code, ASCE 7, has a large table of allowable lateral force resisting systems available to the design engineer. It limits design choices to reliable, tested, and robust lateral systems. Design requirements for these listed systems is provided in the USA Equivalent Material Design Standard. The list is reasonably comprehensive. It's quite long, and it does include mixed material or composite systems. It has very clear limits on the use of certain systems. A designer can use an ordinary steel moment frame. So for us, that would be a nominally ductile, so pretty low seismic capacity steel moment frame. They can use that in a high seismic zone. However, there are very clear limits on height, how high it can go, and weight, what it can hold up. You can't hold precast concrete panels up with such a frame. Look, it's not all green on the other side. The content of these tables in the US is very contentious, from the process of how they add systems to the tables to the values for ductility assigned to each system. Let's now take a look at the design steps for a lateral force resisting system. If we take something as common as a plywood shear wall, in New Zealand, the engineer must design every component from first principles. Listed here is the design steps that we follow from NZS 3603, from nail shear capacities to checking the plywood sheets in plane. For example, each component is checked and designed so the engineer then comes up with a system. In the US, the engineer selects a system from a table. If I need 8 kilonewtons per metre, it tells me that my system involves using 9mm ply lining on timber frame wall with 2.8 diameter flathead nails at 150 centres, with a safety reduction factor then applied. The USA standard for this simplicity does, however, require the designer to think more about how the wall system overall actually works. What's needed for the wall? Is it a standalone full height wall? Does it do force transfer around openings? Is it a punched shear wall? How's it working? What are the collectors doing and how are things joined together? So more of a systems focus as opposed to component design. And the New Zealand design process is becoming more complicated by the recent publication of the updated Timber Design Standard 1720.1, which is requiring more complicated and iterative first principles equations. And the question must be asked if the more complicated New Zealand process is providing better design outcomes for buildings in New Zealand. What about mixed material composite systems? In New Zealand, without a limited or defined list of lateral force resisting systems, there's no prohibition on an engineer attempting to design their own composite lateral force resisting system. This building that you can see here is a real example of a composite system that is made up of a part steel, part concrete panel forming a frame. This building was designed, consented and built in 2011. It was later deemed potentially earthquake prone under the previous EPB system. In comparison, the USA provides an acceptable list of composite lateral force resisting systems within ASCE 7, and the design requirements for the composite systems on this list is provided within one of the material standards. One of them takes ownership for the system and provides the overall system design requirements. It's interesting to note that under the USA system, that previous example of the New Zealand attempt at a composite system would not be permitted. It's not a permitted system. What about the design of some of our building parts, such as a wall out of plane? In New Zealand, even a simple element like deriving loads for a wall out of plane requires some reasonable maths and interpretation of a standard for what is, you have to admit, a pretty common feature in pretty much all buildings. In the US, it's a simple formula of a portion of the short period spectral acceleration with an importance factor modifier. What about the requirements for the anchorage of walls out of plane? Again, in the American standard, it's a very clear equation with requirements spelled out on when an engineer must check bending of the wall between anchorage points. If the spacing of my anchors is greater than 4 feet, I must check the bending of the wall between the points of anchorage. Some people call this prescriptive, but I think it's just clarity. And in New Zealand, even with our standard, with more equations, it was so unclear if parts applied to walls out of plane that it took a determination to confirm how we are meant to derive loads for this common feature. In New Zealand, we have a system where components are certified, marketed and adopted by engineers. However, their use in a seismic system is either not fit for purpose or poorly executed. We have code marks issued for systems that then seem to sit outside the available verification methods. If we compare this to the pre-qualified connection system that's used in the United States, this is connections that are pre-qualified and designed to ensure that they meet the inelastic rotation requirements of a specific lateral force resisting system. We know that if we follow these procedures, these designs will work. What about geotechnical? Foundation design has the same framework of acceptable solution, verification method, and alternative solutions. But again, I'd like to focus on the verification method, same as I have for structures. For something as critical as foundations, as important to your building as the ground beneath it and the design of that, the confirmation of the ground model and soil parameters is outside the scope of VM2, the verification method. In VM4, which is now VM2, safety factors were meant to be approved by the territorial authority, which does not and did not happen in practice. And I note that this is not in VM2 when it was updated, it's been removed. It's also a point to note that the safety factors clash with the geotechnical modules and they're non-conservative in the verification method. For foundation design, we do have the acceptable solution NZS 3604 for timber frame structures. 3604 defines limitations on use, both relating to the structure and the ground. It sets out requirements to confirm the soil parameters and provides lower bound bearing values. But once you step outside of 3604 and you put a verification method structure on the ground, the compliance pathway becomes a lot more murky. We compare this to the US. In the IBC, they have conservative presumptive bearing values, lower bound, appropriately lower bound, and conservative bearing values across different soil types, which at least sets some consistency in the industry and acts as an encouragement for clients to engage with geotechnical engineers to be able to let their structural design be more economical and efficient in terms of their foundations. The safety factors are provided in ASCE 7, so everybody's working to the same safety factors. So why is seismic design in New Zealand so hard? Why is it so hard? We allow engineers to configure the lateral force resisting system with their choice of members and materials. This leads to systems being designed, consented and built which have never been tested, either in the laboratory or in the field in real earthquakes. The building in this photo started to fail in a 6.3 aftershock in Christchurch, and I found it interesting to note that it too features a partial steel moment frame connected to precast panels forming a frame. We ask engineers to complete first principles designs of common systems, to the detriment of focusing on the system behaviour. We expect engineers to complete first principles designs of critical connections. We expect engineers to design for ductility while not providing clarity on how for common lateral systems. For a simple timber portal frame, what mechanism should I be designing for? Do I use flathead nails yielding at the knee joint? Should I use a plywood gusset or steel plate gusset? What detailing do I need to use to make sure that the joints do not lose integrity under repeated reverse cyclic loading? Do I protect my connections to the foundations? What about at the apex? Is there special considerations for the timber sections? If I should use glulam or LVL or probably not ply box beams? It took over 20 years of research and testing before industry adoption of an EBF, yet the New Zealand design engineer is expected to configure their own lateral system, identify the capacity protected and potential ductile elements and successfully apply capacity design. We don't provide a clear verification pathway for foundations for even the most humble of structures. And in some cases, we require complex or ambiguous load derivations for very common situations. And when you step back, we're asking every engineer in every office across the country to solve the same complex problems from first principles every time. And is this system working? At best, our system is leading to inefficiency, but at worst, it's leading to mistakes. We are seeing poor lateral force resisting systems being designed, reviewed, consented, and built. The building code objective is simple. It's to keep people safe. Engineers translate the building code objectives into life safety performance requirements. We look at collapse margin ratios and annual individual fatality rates, and we turn this into a design standard. And we do all of this so that people who use our buildings can do so safely. So what do we need? What do we need? We need a verification method that the average competent engineer can use for the majority of buildings that leads to a structure that meets B1. And to do this, we need the average competent engineer at the standards committee tables, working together with industry experts and academic researchers. And this can be a problem. The engineers designing everyday buildings are not typically well represented in the standards process, not because they don't want to be, but because of time and commercial constraints. And if I pull on some anecdata, it can be quite intimidating for an engineer from a smaller practice to contribute to standards committees with very strong interests present or industry leading persons with more technical qualifications. A verification method should be provided with the primary consideration of achieving the building code objectives for the 90%. The aim of such a method would be to provide a clear compliance pathway for the 90%, making it clear for the designer what they need to do, what they're trying to achieve. This method could be specifically for low-rise buildings. However, it's likely this approach would also suit higher-rise structures, as is the case in the USA. So what would this look like? Lateral force resisting system configurations should be limited to those that have demonstrated robust performance and clear design pathways through either international experience and design standards or through local research. Design engineers should be provided with prescriptive, clear structural design requirements for each of the listed lateral force resisting systems. These requirements should clearly describe the basis of design, the configuration, limitations of use, and the acceptable means of achieving a defined level of inelastic deformation capacity. If we look at the different ways we can provide someone with the information to bake a cake, we can give them first principles component information. We can tell them all about eggs acting as a binder, sugar adding sweetness. We can tell them about dry to wet ratios for mixing ingredients to come up with a cake. Or we can do what we know works best and provide them with a prescriptive method that we know that if you follow this process, you are going to get a banger of a cake. And for our structures, we have the same option. We can give engineers first principles information on components and materials, or we can provide a prescriptive method that we know is robust, that we know will give you inelastic deformation capacity, and that we know will perform. This type of targeted verification method for common systems would provide, in my opinion, significant benefits and increased efficiency, which we desperately need for our construction sector. The natural criticism of this type of approach is that it may encourage engineers to turn their brains off, but I'd argue that it makes it easier to get it right and leaves more time for actual engineering to focus on the important things like load path and coordination with the architect and contractor. How are my services reticulating through my building? How are my diaphragms working? How is my actual overall building structure coming together? And all the other things that I need to do as an engineer to make sure that a good building is being built. And a reminder, I'm talking about the 90%. A pathway will always exist for doing a more bespoke approach for outside the box. Regulators would have clearer boundaries, enabling more consistent risk-based consenting. Design processes could be standardized, freeing engineers up to focus on those things I was talking about, on getting the overall system right, not the minutiae of design. Builders and fabricators would definitely benefit from consistent, pre-qualified details, as opposed to the current situation. You go and talk to any steel fabricator or builder and they will tell you each engineer does things differently. He's giving them different details with different requirements. If we had consistent pre-qualified details, it would improve our efficiency both on and off-site. Peer reviews would become simpler and less subjective, with less reliance on an individual's interpretation of component design requirements within a system. Clients would have greater confidence in what they're getting. They would know that they're getting a robust, well-tested system with a clear design pathway. Most importantly for us as engineers, we would have a clearer pathway to good design, with fewer opportunities for error and more time to focus on the fundamentals that really matter. We can do this without inventing the wheel again. New Zealand is a small country. We have limited resources, and as much as possible, we need to leverage off all the hard work that our international colleagues have already done and look at international standards. We often think of seismic design as a purely technical problem, but it sits within a regulatory system that exists to serve New Zealand society. So it's not just a technical problem, it is societal. We've already seen recently what happens when a technical system doesn't deliver the outcomes that are understood by society, trusted, or seen as fair for the majority. The earthquake-prone buildings framework is a very clear example of this. The percent MBS system, while technically grounded, became seen as inconsistent, misunderstood, and ultimately seen as not fit for purpose in the eyes of society. Central government released the cabinet paper on focusing the earthquake-prone building system when the proposed changes were announced. And this paper repeatedly points to buildings in the 90%, low-rise regional buildings that were technically assessed, but still seen as evidence that the system wasn't working. So despite being technically sound in the eyes of the public, the system was not working for the 90%. And when that happens, the system doesn't hold MB steps in and changes it. And I think there's a clear lesson in that for us as engineers. If our design standards are too complex, too variable, and too dependent on individual interpretation, and too many mistakes are being built, then we shouldn't assume the system will stay as it is, and nor should we want it to. In my opinion, the current system isn't working well for the 90% of buildings. It's not working well for us as engineers, nor for BCAs trying to regulate our designs, or for the building owners. Certainly not for these building owners. Alistair Kadanak spoke at the conference about the risk of trust in our profession. And it made me reflect. After Christchurch earthquake, one of my clients told me that you engineers are kings now. And it's not hard to see that there's been a slow erosion of trust in our profession over the years since, with the press around poor designs and the shift in the EPB system. If we don't take the opportunity to look at how we are doing things, how we're designing our buildings, and to try and make it work, the regulator has shown that they can and will redefine the system until it does. Our measure of success lies in where the rubber hits the road, what is actually being designed and built. Because in the end, it's not the theory in our standards that matters, it's what's actually getting built. Thank you all for joining me. And I'd like to encourage you all, as we have time for a discussion now, I would like to encourage you all to please share your thoughts and opinions. I am one voice, one person, and this is one opinion. So please, there's a survey. It's very short. I promise it's short. You'll get told it's short lots of times, but this is a short survey, and I really encourage everybody who's online today to please take the time to drop in and share your opinions in this survey. It's being hosted by NZSEE. If you're a member of another collaborating technical society, CSOC member and NZGS, and you or your company has an opinion, I implore you to also please reach out and get in touch with them and share your thoughts on this. But if you can do the survey as well, so we can get a large capture of opinions. But thank you all for making the time to join me today. I do really appreciate it. Waiting for, yep, there we go.
Okay, thank you. Thank you, everyone. And thank you, Michelle, for such a clear presentation. So open up for questions. There are a couple of comments, Michelle, in the Q&A section. And if there are any other questions or comments, please put that in the Q&A section.
Okay, shall I? If I think I can answer it, I will. What do I say to those that claim the prescriptive approach prevents innovation? I think that every engineer operating in America that has such a population and diverse approach to what they're building would disagree with that. Innovation is always allowed. We always have alternative solutions. At the moment, all I see with this idea that we're preserving innovation is that we're making it so hard for those of us that are trying to do normal buildings. I don't think that it would prevent innovation in our structural systems. Okay, there's another question here. Why do I think that New Zealand has such a low appetite for standardization? We see the reinventing the wheel bespoke approach in New Zealand across many facets. I mean, that's an interesting question. I think it's maybe not until you start looking at other approaches in international jurisdictions when you realize potentially that New Zealand does have such a low appetite for standardization. I don't know if it's a low appetite or if it's just not enabled in our compliance framework. But I'm very keen to hear what everybody thinks, which is why I'm leaving this QR code. Okay, I am trying to get through the Q&A, sorry. Okay, hi, thanks, Michelle. I agree we need some efficiencies in our system. Am I proposing to remove the current approach for those that are experienced and able to do so, or just add this approach as another potential solution? I mean, at this stage, I'm gathering feedback and thoughts from everybody. I think that there is a pathway forward to allow a clearer or more prescriptive pathway for common lateral force resisting systems whilst allowing the current approach for different things and more innovative things. Barbara, did you want to jump in with some? Please feel free.
No, keep going.
Oh, okay, sorry. I'm just after interviewing a lot of graduates over the years and reflecting on my degree, do you think the BE degree sets up graduates well to deliver on this 90%? Potentially, but there is also gaps that industry needs to step in terms of training. And this is something that I'm talking to CSOC around how we can make sure that we have tailored training for everybody from postgraduate to those of us. Like, I happily admit that I don't know everything, and I'm very happy to do more and more training. So very keen to also see what our profession feels about this, because what we want as a profession feeds back into what the universities then provide for their students. Another question, can we have the American standard as an alternative solution for buildings and make some fine tuning to match with the local standards? I think yes, probably. I mean, our concrete standard is based on a now superseded version of their concrete standard. And I believe there's some discussion around looking at how we could potentially do that. Be great if we could encourage them to come to the metric system and ditch imperial completely. But I think that yes, there's definitely a pathway there to do something like that, to look at international standards, and not just the American ones, Eurocode where appropriate as well. I think I've answered that one. Sorry. Okay, another question. At what point should New Zealand adopt international standards? We seem to pursue this New Zealand best mentality, but we don't have budget or resources to maintain our own New Zealand standards. For example, Eurocode plus national annex allows use of international design tools and techniques. And this is something that I agree with, that we should be looking at. If you have these opinions or you agree with that survey, please share that opinion, share these thoughts, so we can have this discussion. Okay. Thank you, Richard. What are the differences in the end product between the examples of New Zealand and US? One criticism of a more prescriptive approach would be a result in more similar appearance in construction. Have I seen this? My reflection on the New Zealand industry is that we love innovation and the ability to do anything, plus the ability to please clients and architects by achieving the unique. Reminds me of the saying, just because you can doesn't mean you should. I don't think it would result in more similar building typology. You can have similar lateral force resisting systems with very different architectural envelopes. Having spent some time talking to my colleagues in the US, there's still a big variance in what they're delivering in terms of the final product, aesthetically and visually. So the same lateral force resisting or similar lateral force resisting system doesn't mean nothing different or that everything's the same. New Zealand loves innovation and the ability to do anything. I would suggest that New Zealand BCAs don't love our ability as engineers to think that we can do everything, and neither do the clients, who are unfortunately don't understand that we have this ability to pick and choose what we're doing, and can lead to some poor outcomes. Graduates, sorry. Can I see MB adopting these changes in the near future? Look, I'd love to have a conversation with MB. I think if I was MB, I'd have a very strong opinion about this. I think that if I was the regulator, anyone working in BCA, would have a very strong opinion about this. But I'm really keen to talk to my profession first, to talk to all of the engineers involved, and get their thoughts and feedback. We have a lot more chance if we're going to talk to the regulator if we talk with a consistent voice. So that's why we're really keen to get your feedback.
Michelle, there are some comments in the chat as well. I mean, one of it
Please,
is,
yes, jump in.
have you done a design and cost comparison between a typical New Zealand building and US standard?
Yes, I've run through a few comparisons. I've played a little bit more in the timber frame section with that, and also done a comparison between our version of 3604 and their version, the IRC. It's a slightly different process that they do have for something as simple as a plywood shear wall. And I do encourage you, if you're designing these, to splash out and spend the $70 US. Okay, that is a lot of New Zealand dollars with our ratio at the moment, but $70, you can buy the Seismic Design provisions for wood structures from the US. And it's a nice clear document that actually talks more about the system. Do you have a full height wall? Is it a punch shear wall? Are you designing force transfer around openings and considerations? And it'd be good just, you could have a look at it. It's not very long, but it's a compliance pathway. It's not a guidance document. I'm not after guidance. I'm talking about compliance. I have had a look at their steel standard, and the simplicity in the requirements and how AISC 341 is laid out makes it quite clear. And this is sort of what's inspired me to give this talk. Another question here about how do we get more practical engineers on code committees, as there appears to be a large number of academics who have vastly different approaches to structural design. Is it a case of getting more funding to allow a wider range of small and medium consulting firms to commit resources? It's a really good question, Ashley. A really, really good question. And it's something that I'd be very keen to discuss further with Standards New Zealand and MB. We do need practitioners on these committees, or we'll have documents that we can't use as practitioners. We need to have researchers to make sure that all the good information they have, the specialist technical information, can be fed to us so we can understand why the constraints are what they are. But if we don't have practitioners, we're never going to get a good document. So I don't have the answer on that yet, apart from saying I agree we need more practitioners, and I'm keen to put that in the survey, please. Make that a point as well, so I can then carry that through. Materials. There's a question here, why does New Zealand with the population of Sydney need our own bespoke material and loading standard? They are based on other countries' design standards anyways. So there is, in terms of our loading standard, we do have a very interesting hazard. So I understand that. In terms of our material standards, that's what I am encouraging, that we start looking at not throwing everything away that we do here, but what's the efficiencies or good things that we can take from international standards to make our design process better and more fit for purpose. Thanks, Michelle. From a geotechnical perspective, thank you for joining, geotechnical engineer. Considering that geological risks vary across regions, what is my opinion on simplifying the system to ensure code compliance? We obviously need to update the verification method. VM2 is very out of date. And to provide some information, I'm not going to lie, geotechnical is a tough one. That's a tough nut to crack, right? Like, it's so variable, and it's very difficult to wrap a verification method around something as complex and variable as the ground. But there is avenues and pathways. If we again draw on our international colleagues, you could have a situation where it may be appropriate to have a verification method for foundations that's suitable as long as your site and loading from your building meets certain constraints, like 3604 loadings on 3604 ground, but for a lightweight steel shed, for example. Or you could have a pathway where the structural engineer needs to have their ground model and soil parameters confirmed by a geotechnical specialist, but then the structural engineer can go and use the verification method to design within certain constraints. The next step beyond that, obviously, is when you start talking the modules and you have structural and geotechnical working together, and it's more complex, and you need to do that. So there's pathways there. There is different pathways there, and very keen to see an update to VM2 that the geotechnical people are happy with as well. I don't know if I'm keeping up with this, Brava. Mark Ryburn, thanks, Michelle. Can I encourage people to use the public consultation phase for standards? All comments are considered by the committee, even if not able to be taken on board. All comments are critical in informing the scope of future standards development. So that is an important point. Perhaps, Mark, I'll confess, am sometimes not the most diligent, just because it's difficult to pass a document and still you start to play with it a little bit. But if I can encourage people to definitely throw your opinions out there, especially those of you like me from smaller companies doing normal stuff, please. Robert, did you want to share some from the chat while I try and digest some more of these questions? Or
So there's a comment saying designing how a building goes together usually relies on much more than just the numbers. Prescriptive solutions often won't fit.
okay, sorry, I'm just trying to keep on top of these too. Please bear with me. Do we need to start from updating the university curriculum for civil engineering students? I mean, that's quite an undertaking. The fundamentals are still the fundamentals, but it is, I think we as a profession need to figure out what we think is a good way forward first, and then we can start engaging in these discussions with universities, with the regulator, and see where we go. I'm a big fan of getting some education for fundamentals for practicing engineers, and would love to see some of it mandatory, which is not a popular thing amongst the CPEng processes. Could we just develop additional acceptable solution pathways for concrete and particularly structural steel systems like 3604? B1 VM1 can remain for the innovation, but standard solutions would exist for normal stuff. And look, this is an idea that I've thrown around, but I think it's not an acceptable solution. I think we're talking about the same thing, but it'd be verification method, because an acceptable solution provides prescriptive details, like you do this, you put 2 nails in at this solution. If you have a look at, just as an example, the seismic design provisions for wood structures that I'm referring to, it is still a verification method. It still does require an engineer to be an engineer, to apply methods, calculations, and consider the system and stiffness compatibility. But it could sit as a companion document or its own verification method potentially. Absolutely. I think we're saying the same thing potentially. Why is New Zealand not developing design guidelines for various structural components with practical examples, like in the case of US design guidelines by ASCE? Yeah, no, fantastic. Yes, I would love that. That would be great. I would like to see pre-qualified connections that actually account for inelastic rotations. And when I have some idea of the thoughts of everybody in the profession, I would love to start engaging in those conversations about how we do that. I believe this discussion needs to go on after this webinar is finished. How do we do this? It's a good question. In the first instance, I'd really appreciate it if you could complete the survey. If you're a member of either of the collaborating technical societies, it would be great if you also shared your opinion, even if it's just a quick email saying, watch this webinar, agree in concept and principle, and are really keen for CSOC, NZGS, NZSEE to further this discussion, even just to get that initial consensus or opinion going. That would be really good. Do I have any solutions to the problems I've identified? I believe I do, but I'm just one opinion. So I would like to see like I suggested, I would like to see a list of common and acceptable lateral force resisting systems. I would like to see clear design requirements for those systems in the material standards that tells me what I'm trying to achieve and how to do it with some clarity. I realize the devil's in the details though. And I can't do it without, we can't do this without a lot of feedback from other practitioners. Okay, so I'm trying to get through these. Barbara, please feel free to jump in at any time. As an engineer who supports councils with consent compliance, I see huge issues on the design of retaining walls without a clear pathway CSOC has created and is creating documentation, but they run contrary to MB guidance and some still use bronze. I'd say this is a clear case for the issues. Can CSOC not force MB to put a line in the sand and then update the RW from 4429 to reflect this? There is a big issue with retaining wall design and the murky examples, absolutely. As someone who tries to design basement retaining walls in houses integral with the house, it is an area that needs some urgency to be addressed. I know that doesn't provide an answer, but it is something that have raised recently and am raising with the powers that be. But please put that in the form too, because it's nice just for somebody else to say, yes, they agree this is an issue. Okay. I can't keep up with all these chats. It's really great to see that people are engaging. Thank you all. Like the IBC and UBC, New Zealand doesn't have any specific one single code. Fragmented seismic guidelines and information make the seismic design complicated and difficult to adopt. Look, the fragmentation of information, I think, is definitely a challenge. I mean, even working on something as simple as engineering design in residences, there's a lot of information scattered about between the compliance pathway, brands guidance, proprietors or manufacturers information, and it does make things really, really challenging. So please, when you fill out the survey, make sure you include that as a comment. Designing how a building goes together usually relies on much more than just the numbers. Prescriptive solutions often won't fit. Interesting. Perhaps the gap between the academics and the practical engineer is just too big to bridge at an intellectual level. I mean, I'd hope not. I'd hope that we can communicate as a profession and try and share the problems we have. I know as a practitioner that I have challenges and problems that I'm going to be asking researchers and academics to help me solve. I think that New Zealand would benefit from a lot closer linkages between practitioners and researchers, academics. It seems to be a lot stronger with the ATC in the States and how that operates. And maybe it's something here now that we have Bridge established. If you haven't heard of it, please Google it. But now with Bridge established, we may end up with stronger linkages between academics, researchers, and practitioners, which would be a really positive thing, I think. It's a question asking here, is the earthquake-prone buildings register up to date? I'm going to defer that question to MB. It's not a point that I want to get into in detail, but the legislation hasn't changed, don't forget. The cabinets have indicated that it's going to change, but at the moment we still operate under the current system. Martin, oh, hi Martin. Thank you for joining in. Love your webinars as well. Considering that we have more than 400 people attending this very relevant webinar, we need to follow up on this issue. What would be the next steps? Yeah, really, really good point. So if you can, as a very much a starting point, please fill out the survey. Take the time, it's short. If you have strong opinions on this, and I'm seeing that people do, please get in touch with your collaborating technical society. Take the time to flick them an email, let them know your thoughts, and then I believe the collaborating technical societies are looking at coming together to discuss this and figure out what they may like to do as a next step. I feel like we've gotten to the end of it, Brava.
Yeah. I think we have had a good number of questions, and thanks, Michelle, for answering that. And I think we'll bring that to a close. But I would like to encourage you to fill in the survey, because I think, as Michelle said, if we want to take it further, we need some hard evidence that people are supportive and what their views are, because at the end of the day, we as technical societies are reliant on our membership and the views you express, so that we can help push for changes which improve the system. So yeah, please do the survey and also share that with your colleagues where you work with so that others can also fill up the survey. We will this is being recorded, and we will share the recording so that people who have missed the presentation today can also have a listen to it and express their opinions. So while it's fresh in mind, when you have heard Michelle's presentation, encourage you to do the survey before you forget and before you forget the issues which come to mind. So, Michelle, thank you so much for coming forward to raise this critical issue, which affects a vast majority of practitioners, as you mentioned. And we, as a technical society, and technical societies are keen to make sure that we have a system which is fit for purpose for practicing engineers. So I would I support people raising these issues so that we can help address this. So thank you very much, Michelle, for presenting again at this webinar. And also thank you for the 509 odd people, which I saw who joined today to listen to this webinar. Thank you very much. And we look forward to hearing from you all and also working together with you, Michelle, to see what improvements we can help facilitate and make. Thank you
Thanks,
very much
Brava.
for everyone joining. Yeah.
Thank you all. Thank you very much.
So with that, we'll bring this webinar to a close. Thank you very much.